In this lecture, we're going to look at critical exponents and universality, and also at first order phase transitions. Right, so first for critical exponents and universality. This is an important topic in modern statistical mechanics. Right, so if you at a critical point where you've got a phase transition, you look at the thermodynamic quantities as a function of temperature, and we're going to define this sort of reduced temperature, T minus Tc on Tc. Okay, where Tc is the temperature and T is the temperature. If you look at them, what you normally find is there's a smooth part and a singular part. So if we plot, for instance, maybe the heat capacity versus T, you find that around, say, T equals 1 here, which is where this transition, will T equals 0, in fact, T equals 0, where the transition would occur, you'll find the heat capacity might look like this, okay, and it might have a singularity just here, plus some smooth bit, okay. So the singular part always behaves as a power law with some exponent. So we'd normally write this as some constant times T, the difference between the temperature and the critical temperature, divided by the critical temperature, to the P. Okay, so we'd write it like that. Okay, oops, sorry. That'll be what it looks like. And this constant A here can be different on either side of the transition if you like, but the power P is the same either side. So either side, as you go through the transition, you get the same power. Okay. In fact, A could be 0 on one side, so you could have a situation which looked like this, where it went from the looking like that to that, if you wanted to. Okay. So the power P is the same on each side. And we give these things specific Greek letters, alpha, beta, gamma, etc., depending on what's being measured. So, for instance, if you measure the order parameter, the relevant critical exponent is called beta. If you measure the heat capacity, the relevant exponent is minus alpha. And the susceptibility, which is how the order parameter varies with the applied field, if there is an applied field, is minus gamma. So there are all these different things you can measure. Okay. Now, there are several other critical exponents which we're not going to deal with, but let's just deal with the 3 alpha, beta, and gamma. So for the mean field model, which we've looked at, you can actually calculate these things exactly. Beta's a half, alpha's 0, and gamma's 1. So alpha is 0, which means the heat capacity doesn't vary for a second order transition, and we know that means there's no latent heat, and the heat capacity doesn't jump at all; it just varies continuously. And beta equals a half tells you how the order parameter varies, for example. So we know it looks a bit like this. So that's a typical beta equals a half behavior there. And gamma equals 1 means we've got the susceptibility. Now, we haven't really talked about susceptibility very much, but gamma equals 1 for the mean field system we've just done. And these critical exponents allow us to divide the system into what's known as universality classes. So what you do is you take systems with quite different Hamiltonians, but they may have, in fact, the same behavior at their critical points. Okay, as their critical points are approached, and they will have the same critical exponent. So you might have a completely different Hamiltonian for two systems, but as you approach the critical point for either of those systems, what you find is they behave in the same way as far as their critical points go. And therefore we say they belong to the same universality class. Now, this universality class might depend on the dimension as well. You know, it's in 3 dimensions or 3 dimensions or 4 dimensions or something else. So, for example, the Ising model in 2D is in a different universality class for 3D or 4D. Okay, in 4D we know it becomes mean field. Okay, so we know this. Things depend on which dimension you're in. Okay, so we get some examples of universality classes and critical exponents here. Here's the definitions again. Mean field one we've just done. Alpha is 0, beta's a half, gamma's 1. We've just solved that one. I think you've seen the 2D Ising model solved. And in those cases we have alpha equals 0, beta equals gamma. So beta equals 1/8 and gamma is 7/4. Those results are probably due to Onsager, who solved the 2D Ising model. And if you want to project, the 3D easing model hasn't been solved exactly, but we know what the critical exponents are roughly, and that's what they look like. Okay, so if you found something that's where the critical exponents were that, you would probably say, oh, that belongs to the 2D easing model class. Okay, that universality class. If you find critical exponents looking like this, then you're in the mean field class, the universality class. All right, so enough of that, but for all models there is an upper critical dimension, okay, at and beyond which the system will exhibit mean field behavior, which is the kind of behavior we studied in the last lecture. Okay, it's the last video. So for the easing model, that is d equals 4. So if you're in d equals 4, 5, 6, 7, 8 dimensions, whatever, however far you want to go up, the easing models give you mean field exponents. Mean field works really, really well in those cases. In fact, exactly. Okay, so the upper critical dimension for the easing model is 4. Okay. Now this cataloguing of things into, you know, let's go back here, into discrete universality classes where you have very clear-cut critical exponents, which are just ratios of integers, seems to work very well. Unfortunately, it doesn't quite work perfectly. And in 1971, this chap called Rodney Baxter, who's at ANU, came along and solved what's called the 8 Vertex model, which looks like this. You can read about it elsewhere. And he showed that in this model there's a parameter, or probably more than one, you can vary. Okay? And as you vary that parameter, you get critical exponents which vary continuously with the parameter. And so therefore, you don't necessarily have, for all systems, this nice discrete boxes you can put them into. It's a bit hazy. This one changes its universality class depending on exactly what the parameter is, and it changes it in a continuous way. It just drifts through them, which means the whole idea of universality classes is not useless, but it has its limitations. Now, let's look at correlation functions, particularly as we approach the critical point. So, mean field theory, which we've done, assumes uniformity, okay? But in fact, of course, for a real system, there are always non-uniformities. Now, those non-uniformities tend to be damped out by the grad phi squared term in the Landau energy, but they're still there, okay? So, we can look at non-uniformities in our system. So instead of having a system which has all the way across, it's going to look like this, phi versus, say, x in one dimension. It might look much more like this, where you have this thing and jumps to there, down a bit, and jumps up again. It might look something like that, or it could, you have up spins and down spins, etc. Okay, so we can look at non-uniformities by introducing a correlation function between 2 points, x and y. This is in one dimension, but it's applicable to any dimension. 2-point correlation function g of x of y is the correlation of phi x phi y minus phi x average phi y average. Okay, if there's no correlation between these things, there's no correlations in the system, then that's equal to that, and g turns out to be 0. Now, for reasons which we're not going to go into, for large separations, we expect the correlation function to die exponentially, with the distance between the 2 points, and with some kind of length, the correlation length. Okay. Now, that correlation length we need to calculate, and to do that, what we do is we put a point external field at the origin, h of x. So there's our point external field. It has magnitude h, and it's just a point. D is the dimension of our system. And this is a d-dimensional delta function. So we just take the system and we put in our system here, we just put a perturbation, a delta function perturbation in the middle. Boom. Okay. Now our Landau for energy functional is the same as it was before, except we're allowing now for spatial variations and in fact a field if we want to have a field. No, there's actually no field. We've just got a field which is only valid at one point, right? At one singular point we put the field. So we've got a spatially varying field here. The rest of the system has no field applied at all, but only at this point do you have a field. Neglecting this term, the mu0 term, because phi to the fourth is going to be small, and taking the functional derivative, which we know how to do, we get this differential equation. You can test it out for yourself. That's a differential equation we have to solve. In Wang's book, he actually goes away and solves this. You can solve it yourself by just plugging in a solution if you want to. But he gets a solution which looks roughly like this. Okay, it's got some exponential decay and some sort of singular behavior near x equals 0. Okay, and so what he can back out from that is what the correlation length here is. Okay, and when you do that, you find the correlation length diverges as you approach the critical temperature, and it diverges in this mean field case as T minus Tc to minus a half. Okay, so here we go. It goes up here. As you approach the critical temperature, it diverges up. That's the correlation length here. Okay, that's how the correlation length goes. What does that mean? Okay, what does the correlation length mean? Well, basically what it means is if you look at the system, suppose you had a system like this one here where you have up spins and down spins, an Ising type system. The correlation length gives you the size of the black region or the yellow region. Okay, it tells you, how far you have to go before you get uncorrelated with your original yellow and you start to find lots of black. Or you start at black, how far you have to go to find yellow. Okay, so it's basically saying the correlation length is the size of the blocks the system starts to organize itself into. Okay, that's what it means. And the spatial structure smaller than the correlation length, you don't see anything, it's just yellow or black. Okay, so the correlation length diverges as you approach the critical temperature, as you approach where the phase transition occurs. And we can see no details. All we see is big blocks of yellow and big blocks of black. Okay, and what we see in some sense in this system is just the dimension of the space and the number of degrees of freedom in our system. That's what's important here. This is why universality classes occur, because those two things are what's important. The details of the Hamiltonian are not so important. Right, and what else don't we see in the correlation length? Well, this divergence in the correlation length means that intermolecular forces between molecules, there's a molecule here, here's another water molecule, and they might be having some kind of dispersion, van der Waals forces between them. They don't really appear at all. Okay, so what happens is intermolecular forces are very short range. They often decay only as r⁻⁷. So effectively an atom or molecule only sees its nearest neighbours. Okay, in reality, maybe a couple of nearest neighbours, but the range won't get much beyond 10 angstroms. Whereas in a phase transition, you get these patches which might stretch for thousands of angstroms, many molecules. Okay, and the large size of the correlation length in the critical point is caused by cooperative behaviour between the molecules, not by the range of intermolecular forces, which are much smaller. Okay, and this is another example of ignoring the details. It's one of the reasons why StatMech works. It works because we don't need to worry about the intermolecular forces here. We just need to worry about how many dimensions we have, maybe a couple of other things, but not the nature of the intermolecular forces. Okay, number of degrees of freedom is another thing we need to worry about, and this is the particular reason for our universality classes why they work. Okay, because of this, you can ignore details of exactly what force is between hydrogen and oxygen. We don't care. Okay, all right, that's universality classes. Very important part of modern StatMech, but quite difficult to think of problems to do with that. So that's just a description of what's going on. So let's start talking now about first order transitions. So we've done second order transitions. Second order transition, remember, looked like this. The order parameter goes like this. There's no discontinuous jump, but the slope certainly jumps as a function of temperature. Now, first order transitions, which we've met before, look like this. This is a first order transition just here. The order parameter, which is here labelled psi rather than phi, but it doesn't matter, jumps. discontinuously at the transition. This is a second order one, so that's first, that's second, and this is none. Okay, there's no transition here, it's just smooth. Okay, that's a smooth transition. All right, so the first order transitions involve a discontinuous jump suddenly in the order parameter. Right, how do we manage to look at those using Landau-Ginzburg theory? Okay, well, it's actually quite straightforward. We choose a Landau energy functional which looks like this. Okay, so we have here this final term, this 5 to the 6 term, its coefficient S is positive, so we get stability. We don't get something that goes down like this. We're going to get something at large values of the order parameter, which actually goes up. Okay. However, we do have this thing. Unlike in the second order case, this the coefficient of the fourth order term will be less than 0. So mu naught is less than u naught is less than 0, and the first order term, the coefficient of the second order term looks exactly as it did before. Okay, so exactly as it did before. Now let's try and analyze that. If we plot this versus the temperature, what do we get? Well, we get for T bigger than Tc, for T above what we call Tc, which you might want to call the critical temperature, but the transition temperature somehow, you get this graph here. One particular minima at the origin. Okay. For T less than Tc, you get 2 minima, well away from the origin. Okay, so we get that sort of scenario. So let's actually do an example plotting it using Mathematica. We'll choose for our values here S to be 3/4, mu naught to be minus 3/4, Tc to be 1, and let's just try and plot things. Okay, so here's T at 1.54. Here we go. This is the order parameter versus, sorry, this is the free energy. What are we doing here? This is the free energy W phi versus phi. And at this temperature, which is above 1, we get clearly only 1 minima, and the system will sit at that minima. Now we lower the temperature a bit, to 1.26. And what we're starting to see here is a couple of extra minima almost developing. Whether there's a minima, there's another question. I don't think it's a minima, but it's very close to being a minima. So we're starting to see a couple of minima, and they're developing well away from the origin. That's the important thing. Okay. Now, if we go to 1.22, we certainly see 2 other minima developing. That's the temperature now. Okay. And they're not at the origin. But these are not the global minima. So if you ask the system where it would prefer to sit, it would prefer to sit in the lowest point, which is there. Okay. So there's 2 minima there, but they're not the global minima. These are not global. Just here. Not global. This is the global minima. If we lower the temperature down to 1.188, all 3 minima are equal. Ding, ding, ding. Okay. And we have the transition temperature. 1.188. Remember this. So Tc is not the transition temperature. Tc is just an expression here, a temperature which occurs in the system in the Landau free energy, and it's in this case it's 1. Okay. The transition temperature for this case is 1.188. Okay. This defines a coexistent point or line. Okay. So as I said here, this temperature is not the transition temperature. The transition temperature is T star. That's when all of these minima are equal. All right. If we lower T further, we get even more pronounced minima here, and these minima are obviously where the system's going to sit. It's got a choice, but it's going to try and go to the lowest point. Okay. There's still a minimum at the origin. Okay. There's still a local minimum there. But the system tries to stay in that local minima. It'll get kicked out by noise. Eventually noise will kick it out. There'll be some thermal noise which will kick it out into there. Okay, and as we lower the temperature a bit more, this minima still exists, but it's getting shallower and shallower, and these getting deeper and deeper. Okay, if we lower the temperature still more, say to 0.895, this minima at the origin has disappeared. There's no longer a choice. The system can't say, well, I'd like to sit in this local minimum maybe. Absolutely not. It doesn't even exist. It's a maximum now. Okay? And the point where this minima here becomes a maximum is called the spinodal point or line. And beyond this, the disordered phase, this is what they call the disordered phase here. This is ordered here. This is order, and this is disorder because it's got a phi of 0. Below that, the ordered phase does not exist anymore. Sorry, disordered phase does not exist anymore. It has to be ordered. Okay, so in this case, temperature 0.895, we definitely have gone from having a local minimum at the origin to no minimum at all at the origin. All right, so let's look at this system in terms of metastability. So the system here on the left is metastable in the sense that if we start off here at the origin and slowly cool it, these other minima will develop, but you might have to wait around a long time for it to jump into those minima because it doesn't really know about them. Here the order parameter is 0, here it's something like 0.7, and it might take a long time for the system to start exploring and find out, hang on, there is a better place to be than phi equals 0. Phi equals 0.7 is better. So it could be metastable, and it will be metastable in that case. And this is why you can supercool liquids and superheat them as well. You can supercool water, of course. You can try and, if your water is very, very clean, doesn't have any nuclei for nucleation purposes, then you can cool it well below 0 degrees centigrade and it will still remain as liquid water. And similarly, you can heat liquid water up beyond 100 degrees centigrade if it's very pure and there's no way of nucleating sites to form the more stable phase. Okay, so here you've got a metastable system. This one on the right is definitely not metastable. It's unstable. There's no possibility of supercooling this beyond that temperature. It wouldn't work. Okay. So this is what we have for the Landau free energy. For high T, we get this. For low T, we get that. We get two minima. And these two minima have what am I going to say? The crucial point is the two minima appear well away from the origin. So there is a discontinuous jump in the order parameter at the transition point. So a graph of the minimum value of phi versus the temperature looks like this. At high temperatures, we only have the minima at the origin, which is that one. Okay. As we cool the system down, at this point, for example, these other minima start appearing. Okay, so there we get other minimum start appearing. Okay. If we cool it down enough, then this minima at the origin, completely disappears. Okay, so that's definitely where you've got this this spinodal point is here. Okay, and in between somewhere here, the minimum away from the origin will be the one which is actually globally stable. Okay, so there's a strong overlap region here where you've got in fact three minima. You've got the two either side and the one in the middle. And that's what the structure of the thing looks like. Okay, so it's very different from the case of the second order transition. Okay, so we have minima side by side existing, which could be one of them is always metastable. Okay, so let's look at what happens for an external field. Okay, so we're just going to put the same Landau free energy and add in a nice uniform external field. What happens then? We're not going to look at this in detail, but what happens there are two regimes. If our field is low enough, the field just rounds the order parameter pre-transition. So here's an example of magnetization versus temperature for different kinds of fields, 1 Tesla, 2 Tesla, up to 5 Tesla. If it's only 1 Tesla, what we see is the transition here is rounded a bit. So just here it's rounded, but there's still a very sharp transition. It's still sharp. Okay. However, if we go to higher fields, there is no longer any transition. There's no longer a sharp jump at all, and it's just gradual. Okay, we've got rid of these this very sharp transition. Okay, the minima in fact, in the system merge. And if you plot it in mathematics, you can see that. Okay, so this is a magnetic system with a first order transition for different applied fields, except eventually the first order transition for high enough fields is just totally wiped out. Okay, so that's very quickly, that's what happens if you have an external field, and you can go to Mathematica and play around with it yourself and see what the result is. Okay, so let's have a summary of first order and second order transitions. Here's the first order one here, a big jump. Here's the second order one, no big jump, but a sudden kink. Okay, so first order, what happens? Phi jumps discontinuously to transition. The order parameter jumps in a discontinuous manner, and the minimum at phi equals 0 is still present after the transition, but is metastable. The other important thing about first order transitions is the entropy is discontinuous. Heat is absorbed going from the low T to the high T phase, and that heat is the latent heat, familiar for you for boiling water or melting ice. Okay, and if there is a non-zero latent heat, if you find a non-zero latent heat, the transition must be first order. It can't be second order. Okay, and if the density is our order parameter, then at boiling water or freezing water, you obviously have jumps at these transitions. Okay, so that's obviously first order, boiling of water and freezing of water, because you have a latent heat, and also because if the density is your order parameter, it's definitely jumping. Okay, second order transitions are a lot more gentle. They have no jump in the order parameter, but the derivative of it certainly does jump. But the entropy is continuous, and there's no latent heat. Second order transition, you just don't have any latent heat. So that brings us back to thermodynamics. That's relating all this first order, second order stuff back to our original interest in thermodynamics. And let's finish by looking at an application to particle physics. So this kind of stuff, we have first order transitions, second order transitions, Landau, Ginsburg free energies, is all over physics, not just in stat mech, but also in condensed matter and in particle physics. So here's a paper on the effective field theory and electromagnetic baryogenesis. That means formation of particles in the singlet extended standard model. Okay, so we're going to form baryons in the very early universe. And you can see here, this is a plot of the energy the particles formed versus temperature. And you can see in this case they're both getting first order and also second order transitions depending on what the parameters are in their model. And this is a very, very hot system. This has, 1 EV corresponds to 11,000 Kelvin. So these guys are getting up to about 100 or more GeV, which is about 10 to the 15 Kelvin. And that means they're in the very early universe, just a fraction of a second after the Big Bang. So this is an application of this kind of stuff to particle physics as well. There's applications all over the place. These kind of simple